Welcome. Let's get started. So first off, let's go through some review of some key concepts from your 121 class that are really important in 131. So we're going to tie in some other concepts that you've seen in 121, in our 131 class later on, but these are the ones that are really key for us to move forward. So first off, we're going to go through some common bonding patterns. So that's the what you are probably familiar with is the octet rule, quote unquote. We're going to go over shapes of molecules, which you may be more familiar with in terms of Vespri theory. So that's is something linear, or is it trigonal pyramidal, or is it tetrahedral? That thing. We're going to go through polarity of bonds, and we're going to relate that to atoms' relative electronegativities. We'll go through polarity of molecules, and we're going to do this the general chemistry way. So that's the way that you probably learned in 121. Now, I'm going to introduce a caveat to this right now, and that is that in the next chapter, we're going to learn an abbreviated organic chemistry way. Now, the general chemistry way, we're going to see that it works really well for when we have super small molecules, but in organic chemistry, we're going to deal with much larger molecules. And so it's nice to have a different, and honestly, I think a better way of figuring out if a molecule is polar or nonpolar. And I know that that's something, figuring out if a molecule overall is polar or nonpolar, that's something that a lot of students struggle with. So that's one of the reasons why I'm going through it in this series of videos before we actually get into the content for our 131 class. Once we have that as a basis, we are then going to get into intermolecular forces. So London dispersion forces, dipole-dipole forces, and hydrogen bonding. We are then going to talk about solubility. So you may have heard of that as like dissolves like. So something that's polar dissolves in something that's polar, and something that's nonpolar dissolves in something that's nonpolar, and something that's polar doesn't generally dissolve in something that's nonpolar. And then we'll go very briefly over the definition of acids and bases. So with that, let's get started and go into common bonding patterns. Okay, so again, with this, I'm assuming that you have learned this or something even if you haven't learned it in exactly the same way, you still learned the content, and so I'm just going over a brief review. However, if it's something that you feel like you need more of a review on, let me know. I have a whole series of videos for my 121 class that I can share with you. There are also some great YouTube videos out there that can help you in reviewing this stuff. But again, with this, my purpose is just to remind you so that you can go, oh yeah, I remember how to do that. All right, so first off, we can predict the number of bonds an atom will form based on the number of valence electrons it has. So remember that the valence electrons, those are the ones on the outer shell. They're the ones that do stuff. The core electrons, those are the ones that are buried inside, and so they don't really do stuff. So remember that the valence electrons, we can tell really easily how many valence electrons something has by, most of the time, by looking at where it is on the periodic table. So I'm going to pull up a periodic table here. Okay, so you can see I did not actually pull up a periodic table, but I tried to draw one, kind of. And so if you would like to draw one like this yourself, great, go for it. If you want to pull out maybe a periodic table that you got from your previous class or pull it up on a device, great. So the way that we can tell how many valence electrons there are in something is by counting from left to right, skipping the elements here and skipping the elements here. So these ones are called the D block elements, and these ones are called the F block elements. Okay, so what we're going to do is we're going to count from the left-hand side, so starting over here, to the right-hand side, and so everything in this first column that has one valence electron. Everything that's in the second column has two, then we skip over this middle part, then 3, 4, 5, 6, 7, and 8. Okay, so it's really easy to tell how many valence electrons something has as long as we can count from left to right and skip the D block and the F block. So you can figure out the number of valence electrons that, anything in these two areas, anything that has. In organic chemistry, we see some elements that are repeated often, and so these are some of them. First, I'm going to do hydrogen, and the way that we can figure out that that it forms one bond is by drawing the symbol for hydrogen, which is H, and then recognizing, okay, hydrogen, it's right up here, it has one valence electron, so we put one electron right there. What we're going to do as we go to carbon, and I'll just do that right now. As we go to carbon, it has 4 valence electrons. So for carbon, we put one electron here, 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 and here. So we put a valence electron in each of these 4 positions, so the top, the bottom, and the right, and the left, before we're allowed to do any pairing. Then, once we do that, we think of each single unpaired electron like this as like a hand that's reaching out and wanting to grab. So however many single unpaired electrons you find when you draw this Lewis dot diagram, that's the number of bonds there will be. So for hydrogen, there's going to be one bond, because there's one valence electron right here, and it's unpaired, so it's like a hand that's reaching out to grab on and bond with somebody else. It also has 0 lone pairs, and I'll show you what a lone pair looks like in just a second. So hydrogen overall, when it's bonding, has 2 electrons. And so this last row that I'm going to use, I'm going to have that this is the number of electrons total around the atom when the atom is fully bonded. So when it's fully bonded. Okay, so 2 electrons. All right, so then carbon, we see up here, and actually let me pause for a minute and redraw these. Carbon has 4 valence electrons, and each of those valence electrons is by itself when we draw the Lewis diagram. And so it's going to form 4 bonds and have 0 lone pairs. Oh, something that I should have mentioned is that whenever we have a single bond, that represents the sharing of 2 electrons. Hence why when I had a hydrogen with like that bond shown as a line, that represented 1 bond or 2 electrons. All right, so carbon is going to have 4 bonds total, and I need to redraw that again. Okay, so it's going to have 1, 2, 3, 4. So I'm showing those 4 lines. Remember, each of those lines represents 2 electrons being shared. So we have 4 times 2, so 8 electrons total, 8 valence electrons surrounding that carbon. All right, so next up we have nitrogen. Nitrogen, we can tell it has 5 valence electrons because nitrogen is right over here, carbon is right there. So looking on our periodic table, counting from the left-hand side to the right-hand side, it has 5 valence electrons. So you might be really tempted to say, oh, 5 valence electrons, 5 bonds. No, do not do that, because that is not the case. Nitrogen, when we put the electrons, the valence electrons on it to show the Lewis dot structure, we have to do that thing where first we have to put an electron in each of the 4 positions, and only once we've done that can we start pairing up. Okay? So remember that in our process, nitrogen, in our process, any unpaired electron on the atom is going to be like a hand that's reaching out. But if we have electrons that are already paired up, it's like, well, they're already holding hands. They're already happy. They're not going to form a bond. So nitrogen has 3 unpaired electrons. So 1, 2, 3, like that. And so nitrogen is going to form 3 bonds. We also, when we're drawing it, have to show that lone pair that nitrogen has. So nitrogen has 3 bonds and 1 lone pair. Remember, every bond, once again, counts for 2 electrons, and every lone pair has also 2 electrons. So when we count up the number of electrons around nitrogen, that is 8 electrons total. So we can do that same thing with oxygen. We go oxygen, that's here, it has 6 electrons, so 1, 2, 3, 4, 5, 6. Doesn't matter if I drew the 2 lone pairs here and here, and the 2 single unpaired electrons here and here, like it doesn't matter. So I can have my 2 lone pairs and my 2 bonding pairs. So 2 lone pairs, 2 bonding pairs. Again, notice that I have my bonding pairs coming from wherever I have an oxygen that has, or wherever I have on the oxygen that has a single electron that's not paired. It's like a hand that's reaching out. And so that gives me my 2 bonds, and so I'm getting 2 lone pairs, and we get 8 electrons total. All right, so then finally we have X. Now what's X? Well, if you look on your periodic table, you're not going to find X. You're going to find Xe, which is xenon, but when we say X, usually we are referring to one of the halogens. So that would be that X equals fluorine, chlorine, bromine, and iodine, or iodine. Okay, so X, that's over here. So fluorine, chlorine, bromine, iodine, however you want to pronounce it, that has 7 valent electrons. So we go 1, 2, 3, 4, 5, 6, 7. And so it will form 1 bond because it only has 1 electron that is not already paired with another one. All right, so X is going to look like this. So 1, 2, 3, 4, 5, 6, 7. So it's going to have 1 bond and 3 lone pairs. So overall, there are 8 electrons. So here we can see that there's definitely a pattern. With hydrogen, our pattern is annoying and gets broken because notice that hydrogen only has 2 electrons around it. It still has a full valent shell though. With all of these others, when they have a full valent shell, when they're totally bonded, like as much as they can handle, they have 8 valent electrons, and that is what we know of as the octet rule. Again, I know that I'm blasting through this. If this is something that you need more review on, please let me know. I can guide you to some good resources. So I'm also going to explicitly write this out, that when we have 2 electrons that are like right next to each other like that, that is representing 2 electrons that are unshared. So equals 2 electrons unshared. We also call that, again, a lone pair. And if we have a line, that represents, I'm actually going to make this a little arrow so that it's a little clearer. That represents 2 electrons that are being shared. So that is known as a bonding pair. Okay, what about if we have 2 lines? So 2 lines like this. Well, that represents 4 electrons being shared. So remember that every line represents 2 electrons being shared. And so if we have 2 lines, then that would represent 4 electrons being shared. If we have 3 lines, that would represent 6 electrons being shared. So I think you probably got a lot of practice in drawing Lewis structures, so drawing the structures of full molecules where you're showing all of the bonding and non-bonding valence electrons. So I'm not going to go through exactly how to do that. Again, though, I have old videos from when I taught this previously that I can direct you to. And there are also lots of great resources online that you can use. So let me know if this is something that is foreign or that you feel like you need more practice on. So using these common bonding patterns, please try this out. Complete the following Lewis structures by drawing in all of the bonds and the lone pairs in each compound. So before you do that, what you need to remember is these common bonding patterns. So here you should always have, like when you're drawing a Lewis structure, if you see a hydrogen in there, that hydrogen has to have 1 bond and no lone pairs. If you see a carbon, it has to have 4 bonds and no lone pairs. If you see an oxygen, it has to have 2 bonds and 2 lone pairs. So you're going to use those common bonding patterns for figuring these out. Go ahead, pause the video. This is the first time that you're doing this. Please make sure that you're taking the time to do it. I know that it's so tempting to want to just watch through and think, oh yeah, I got this. But it doesn't work that way. You need to pause the video and you need to try it yourself, and then we'll go through it together. So go ahead, pause the video now, and let's go through it together in 3, 2, 1. Okay, so here are the answers. Notice that with these, I'm always following those common bonding patterns. So for example, let's look at the carbon in A. So the carbon in A. So we know that carbon needs to have 4 bonds around it and no lone pairs. So we're going to count and see that we've satisfied that. So it has 1, 2, 3, 4. So again, this is a double bond right there. Okay, and making that double bond between the carbon and the oxygen is the only way that we can get carbon to have 4 bonds and oxygen to have 2 bonds. All right, so similarly, oxygen, let's go back up and look to make sure it should have 2 bonds and 2 lone pairs to have a total of 8 electrons around it. So it has, sure enough, 1, 2 bonds and 1, 2 lone pairs. Okay. That is it for this video. On the next one, we will go through shapes of molecules, also known as molecular geometry, also known as VSEPR theory. See you then!